The type of refrigerant fluid and the charge quantity are critical factors for air conditioning system manufacturers. They affect the energy efficiency and the consumption of the product. This is why engineering simulation tools like Simcenter Amesim can really help during product development, providing insight into the effect of design variations, different fluids, or technological choices on the machine's performance. We are now inside the Amesim modeling environment. To the right, we have a set of icons, representing components and functional elements that are contained inside air conditioning systems. Every graphical element contains mathematical equations that describe the dynamic behavior of the element they represent. Our sketch area is to the left. We use the modeling elements to build a sketch inside Amesim by dragging them and dropping them from the library area into the sketch one, and then connecting them one to another. Let's fast forward as we continue building the sketch. We are now looking at a complete model of an AC system inside Amesim. Here we have the compressor model, the external unit's heat exchanger, the expansion valve, and here's the internal unit. Here we have the room, this is a wall, and the model includes several layers of different materials and accounts for external solar radiation. The internal air volume is of 600 cubic meters. The model includes a simple control strategy that intervenes on the compressor speed to maintain the target temperature of 21 degrees. Let's move on to the model parameterization. This is a compressor, and to parameterize it, we set the displacement and its efficiency by using fixed values, a mathematical expression, or by importing a volumetric efficiency map that you can quickly get a hold of from any supplier datasheet. After the compressor, we've got the tube and fin condenser. Here we have to parameterize the internal geometry of the refrigerant pipes and the external fins crossed by humid air. If we had a liquid-liquid heat exchanger, we would parameterize the geometry of the exchanger on the water side, for example. Once we've parameterized all the elements of the sketch, we can go into the simulation mode. In this simulation, we assess the dynamic behavior of the AC system over 24 hours in August. Amesim allows us to plot the compressor speed, power exchanged by the condenser and the evaporator, and the power requested by the compressor. Other useful information we can extract from the model is the comparison of external air versus the one entering the room and the average temperature inside the room, or relative humidity. On the refrigerant side, we can plot pressure evolution or the gas mass fraction. Here we can see the representation of the thermodynamic cycle on the Molière diagram for fluid R410A that we are using inside this AC system. Let's say we have to assess the impact of a new refrigerant fluid inside this AC system. This requires a very simple operation in Amesim. We select another fluid from the library and then we add it to the model. Amesim will then allow us to compare the consumption and performance of the AC system with the old fluid and with the new one. Let's look into the Molière diagram for the new fluid that we've selected, R32. Amesim allows us to visualize the new thermodynamic cycle, pressure levels in the evaporator and the condenser. In addition, the user could employ Amesim to assess the optimal charge quantity of the refrigerant fluid or adapt the component sizing to the project requirements.